Assalamu alaikum. This is the first lecture for CS 317 operating systems. It has some introductory material and then it moves on to the first chapter of the course.
My name is Uruj Ainuddin. Some of you know me from a previous course. My job is to help you move through the new system of online education and to help you understand this subject that I love so much. I have taught it many times previously, but never online. So I may make some blunders here and there, and I hope that you will overlook them.
So let us talk about the course. This is the course plan. The topics are Introduction to Operating Systems, Processes, Uniprocessor Scheduling, Threads, Concurrency, I/O Management, File Management, Deadlocks, Networking and Distributed Processing, and the total number of lectures is 30. The complete course profile is uploaded in Google Classroom. These are the books I will be using. Book number 1 is Operating Systems, Internals and Design Principles by William Stallings, and we are going to use the 7th edition. Book number 2 is Operating System Concepts by Silverschatz, Galvin, and Gagne, and we are going to use the 9th edition. And book number 3 is Operating Systems by Gary Nutt, 3rd edition.
There are two course learning outcomes for this course. CLO1, describe the fundamentals of operating system architecture. The taxonomy level is C2. The PLO it is mapped to is engineering knowledge. CLO2 is explore synchronization and resource management issues in operating systems. The taxonomy level is C3 and the mapped PLO is PLO2 problem analysis. We will not be conducting quizzes in this semester. Midterms have not been scheduled yet. So I will set you assignments which you will submit via Google Classroom and I will assign you 40 sessional marks on those assignments. There will be a complex engineering activity. It will involve coding exercises relevant to system programming. Students will be asked to submit a report containing the code. This activity will map to CLO2 of the course. If a midterm is announced, I will incorporate its marks in sessional evaluation. The reason we have a full course for system software is that this is the part of computing that will harness and use the hardware of a computer. We have learned about computer hardware in courses like computer organization and design and computer architecture. We have learned programming and algorithm design as well. Now you will see how all these elements are brought together. If you know operating systems well, I am certain that you will know computers well. Before we move to the contents of the course, let me take some time to talk about the difficult times we are living in. This pandemic has nearly halted life as we knew it. But there is a thing in human nature called hope, and this beautiful thing gives us the energy to keep moving even when the end to our ordeal is nowhere in sight. It is the hope of better days that has turned us towards alternative teaching arrangements. I am sure that you are missing the university, your friends, and your normal routine. It was rigorous and hard, but it meant a lot to you because it was reshaping you into a better and more able person. Online lectures are part of the efforts to bring back the routine that you had. We will do whatever we can to bring back normalcy in our lives. Even though I am not in the same room with you, please remember that I am just an email away. Let us go through this course with full dedication, and you will see that things will become easy and life will get better, inshallah. So, class, let us start the first chapter, which is Introduction to Operating Systems. I am using the William Stalling book and I am referring to chapter 2 of the book. With each topic, I will tell you the book and chapter that I am using as reference. In a computer, there is hardware. What is the most important thing in this hardware? The processor? Right. But why? because it executes all the instructions that are being carried out. What is the second most important piece of hardware? The memory. Correct. Why? Because it stores the instructions to be executed. Now look at the arrangement here. There are application programs which are sets of instructions and they want to execute. What do they need? The hardware. In this arrangement, every application needs to know the hardware and it needs to interact with it directly. If I change the hardware, the application will need to be recoded. Now we bring something called the operating system into this arrangement. The operating system or OS sits between the hardware and the applications. The OS controls the hardware. The applications are coded with respect to the OS. The applications ask the OS to ask the hardware to execute them. So the applications never interact directly with the hardware. If I change the hardware now, I need to make changes in the OS but not the applications. Here I want you to pause the video and write the answer to the given task in a Word file. I am asking, can you define operating system in your own words? See you soon. Let us start with the objectives of an operating system. Have you noticed that people in your family who are older in age and have never had any computer education can easily use a smartphone? Not only that, they do not think it is a difficult task. Why is that? Because most smartphones use an operating system that takes care of the hardware details. These people do not know what processor or how much memory is in the smartphone, nor do they care. This is the first objective of an operating system, making the computer usable for a user who does not know anything about computer hardware. The second objective is to let people use computer resources like memory, input, and output devices efficiently. The last objective of OS is to be able to change and improve as new functions or resources are added to the system. If a new function is added, not only should it be incorporated, previously present services must also be kept available. What are the services that an operating system provides us? Number one, program development. The operating system provides us editors and debuggers to help develop programs. Number two, program execution. In order to execute the application, the operating system loads its instructions and data in memory locations, initializes files and I/O devices, and allocates processor to the application. 3. I/O access. Operating system provides us access to monitors, printers, scanners, microphones, keyboard, mouse, and other devices attached to the system. Each device has its own control signals. The user asks to read from an input device or write to an output device, and the OS converts these read or write commands to device specific signals. File access. Point 4. It keeps our files in a file system and remembers the actual locations of these files on secondary storage. The OS helps us access the files we are permitted to use, blocking us from files for which we are not granted permission. 5. System access. Operating system helps to log into a computer if user is valid. So the OS keeps track of each user's login ID and password and the permissions he has regarding system resources. Number 6 is error handling. If an error occurs, the OS identifies it, notifies the user, and in some cases can also recover files. And the last and the seventh is accounting. Sometimes we need to know statistics like how much processor time has been spent in a task or how much memory has been used by a task. All this data is also tracked and stored by the OS. It can be used to optimize applications. On a commercial multi-user system, this information can be used for billing. To appreciate the role of operating systems in our lives, let us look at the history of computers. If we go through the history of computers, we will find four different types of machines. The most primitive of these is serial processing system, which was succeeded by the simple batch system. Later we come across the multi-programmed batch system, and then the final evolution was that of the time sharing system. Now I am going to talk about each one of them in chronological order. The first era of computing is referred to as serial processing. Once upon a time, there were computers, but they did not have any operating systems to manage them. Computer consoles had display lights. Computers had toggle switches and card readers for input. Output was produced with a printer. Programs were written in machine code on punched cards. Machine code, by the way, is a combination of 0 and 1. There are no alphabets, there are no letters, just binary information. And a stack of punch cards was fed into the card reader. Here you see the first commercially available computer, UNIVAC. Also, you see a punched card containing punched holes. The absence and presence of holes represents the binary information of 0 and 1. I have also included the picture of the early input device, a punched card reader, in which they fed a stack of cards which would be read and executed. In those days, computers were so expensive. They were owned by large companies or universities. People had to pay a fee to use them. There were two major problems with these computers. The first was scheduling or scheduling. Users needed to go to the computer facility, pay a certain amount of money, and get a time slot reserved for their computation. Now, if the reserved time slot was larger than required, the computer remained idle in the remainder of the slot. Let us take an example. We reserved half an hour for our work, but whatever we were supposed to compute finished in 5 minutes. Now, the problem is we paid for half an hour and we have nothing to do with it, so that money is lost. And since we have been scheduled on this machine for half an hour, nobody else can use this machine because this time has been reserved for us. If the time slot was smaller than required, the user would be asked to remove his program input from the computer at the expiry of the slot. He would have to reserve a larger time slot in which he would start from the beginning. This would mean that whatever he did in this reservation was wasted, as was the money that he paid for it. Again, take an example. We reserved half an hour for our computation, but we could not finish our work in half an hour. So at the end of the time slot, we would be asked to leave and we will take all our input punched cards and move out. And then we will make another reservation which would be of a greater duration than half an hour, and we will have to pay the facility another amount for this reservation. And whatever we did in the previous reservation is wasted, the work is wasted, the money is wasted. The second problem with serial processing was the amount of time spent in setting up the machine. Users had to load the compiler, load the high-level language source code. This would generate the object code, then save and load the object file, and then load the library functions and link them to the object file, all of which would involve mounting and dismounting punched cards. If there was an error, the user would have to start from the beginning. So you can imagine that quite a lot of time was spent in setting up the machine. So, in a nutshell, the problems were that computers were scarce, computer time was expensive to buy, too much time was spent in setup, and an error could drastically affect the cost of computation. In order to overcome the problems that we saw in serial processing, we made a program called a monitor, which was meant to manage the computer for us. The user no longer had direct access to the processor. The user submitted his job, the source code, on punched cards, and a computer operator took jobs from different users, placed them one after the other in a batch, and mounted the batch on the card reader for the monitor. Execution began with the monitor, which read the first job and allowed it to run on the processor. The monitor transferred control to the job. This means that the monitor gave the job access to the processor and the job could now execute. When the job finished, control would automatically be transferred to the monitor, or the processor would be transferred to the monitor, and now the monitor would execute, which read the next job and transferred control to it. This continued until the batch of jobs was complete. Now the memory had to store two programs at the same time, the monitor and the user program. Memory locations that contained monitor code formed the system address space. Likewise, memory locations that contained the user program formed the user address space. The monitor had to be loaded as soon as the machine was started and would remain in memory as long as the machine was turned on. It could never be moved out of memory or the machine would not function. So it was called the resident monitor. The monitor could write at any memory location, but the user program could not write in the system address space or the memory locations of the monitor. This feature, called memory protection, ensured that a malicious program did not change the monitor, causing the computer to malfunction. To stop a user job from monopolizing the system, a timer was set at the beginning of a user job. If the timer expired before the job had ended, control was forcibly transferred from the job to the monitor. Let us look at the format of a user job submitted to a simple batch system. Lines starting with the dollar sign are lines of the job control language or JCL. The JCL lines are meant to be executed by the monitor. They instruct the monitor to prepare the machine for a user job. Any line not beginning with a dollar sign is part of the code of the user job. At first, control is with the monitor. $job tells the monitor to fetch a user job for execution. $FTN instructs the monitor to load the Fortran compiler. The monitor transfers control to the compiler and the compiler reads the source code and generates the object code, storing it on secondary storage, which is mostly tape. Then it passes control back to the monitor. $load instructs the monitor to load the object code. $run starts execution of this code on the data input by the user. $run signifies the transfer of control from monitor to object code. $end signals the monitor the completion of job and control is passed back to the monitor. Some instructions which altered critical system registers and handled I/O operations were designated as privileged instructions. Two modes of operation were designated for the processor: kernel mode and user mode. Privileged instructions could only be executed in kernel mode. When control transferred to the monitor, it would switch the processor's mode to kernel and switch it back to user mode before transferring control to the user job. This mode switch could only be done by the monitor. This guaranteed that the privileged instructions could never be executed by the user job. So, in simple batch systems, the processor either worked on a monitor instruction or a user job instruction at a time, but it executed one instruction at a time. All I/O was handled by the monitor only. If a user job tried accessing system address space or executing privileged instruction, control was immediately transferred back to the monitor, and this was flagged as an error. Later computers also incorporated the use of interrupts. Now consider this scenario. I have a simple batch system. I submit a job and the monitor transfers control to my job. My job starts executing and then it asks for I/O. Control is transferred back to the monitor. The monitor tells the I/O device to start the data transfer and then it waits for the I/O device to say that it has finished its work. During the time that the monitor is waiting, what is executing on the processor? The answer is nothing. The processor is idle. This brings us to the third kind of computers in this history: multi-programmed batch systems. Let us first talk about multi-programming. Multi-programming is having more than one user jobs loaded for execution. Mind you, loaded for execution. I'm not saying having more than one user jobs executing. No, I repeat, having more than one user jobs loaded for execution in the memory of a computer is multi-programming, and it is also called multitasking. What we need to note is if there is a single processor, it will execute only one instruction and hence only one program at a time. The next thing that we define is degree of multiprogramming, and this is the number of user jobs that are loaded in the memory at a particular instant. So what we did here in this third kind of system is that we started loading more than one user jobs in the user address space of the computer. Let us take some time to talk about the general structure of a job. Every user job is composed of CPU bursts and I/O bursts. In a CPU burst, the job executes on the processor. In an I/O burst, an I/O operation that the job requested takes place. The red chunks are I/O bursts. The yellow chunks are CPU bursts. Every job starts and ends with a CPU burst. There is a CPU burst at the beginning of a job in which the monitor sets up the hardware for it and transfers control to the job. There is a CPU burst at the end of the job in which it transfers control back to the monitor and the monitor saves whatever is supposed to be saved. For every job, the processor runs in the beginning and at the end necessarily. Every I/O burst is sandwiched between two CPU bursts. Before every I/O operation, the job requests for I/O, the monitor grabs control of the processor and instructs the relevant device to work. After the I/O device completes its work, It generates an interrupt, so the monitor starts executing and transfers control to the job that requested this IO operation. So for every job, the processor runs before and after every IO operation necessarily. Jobs are either CPU intensive or IO intensive. CPU intensive jobs have long CPU bursts and short IO bursts. IO intensive jobs have short CPU bursts and long IO bursts. Look at the job that I have drawn over here. What kind of job is this? And I reiterate that when a job requests IO, the job waits for the operation to finish. During this time, the processor is idle. Now let's come back to multi-programmed batch systems. If you remember, I told you that in multi-programmed batch systems, we start loading more than one user jobs in the memory. So what is there in the memory? There is the monitor in the system address space, and in the user address space, there are more than one jobs. Every user job is loaded in a finite set of memory locations, which forms its address space. No user job can write in the system address space. Additionally, no user job can write in another job's address space. When the current job asks for IO, the monitor selects another user job to execute on the processor. This reduces processor idle time and makes the machine more efficient. A job leaves the processor in two conditions: if it has completed or if it wants to have an IO operation performed. When an IO device completes the designated task, it interrupts the monitor. When the current job relinquishes the processor or leaves the processor, the monitor identifies the user job that had requested the task that just completed and transfers control to this job. I want you to think about how the degree of multiprogramming is going to affect your system. What seems to be the picture is that you are bringing in more jobs in the memory, and when one job says, I don't want to execute anymore, I want this IO operation performed, you take it off the processor and you bring in another job. And the benefit that you're getting is that while one job is waiting, the processor does not remain idle, it's executing another job. My question is, what happens when the degree of multiprogramming is very low? Multi-programmed batch systems were mostly mainframes. That is, they were computers which would support multiple users simultaneously, each with his own input and output device. There was a single processor. Jobs from each user were kept in the memory. At one instant, only one job would execute. All other users experienced a lag in service and had to wait for their turn, which was not a good experience. So, time sharing was a technique created to bluff mainframe users into believing that each of them had a separate processor working on his job only. And this is how it is done. We set up a timer for a period called the time slot or the time quantum. Keep in mind that the time slot is usually a small period. We start the timer at the beginning of the user job. When the timer expires, we take the processor away from the current job, whether or not it has finished. If it has not finished executing, we place it at the end of the queue of jobs that has been submitted. We pick a job from the head of this queue, start the timer again, and allow it to execute on the processor. Let us consider a time sharing system with a time slot of 5 microseconds. The monitor picks a job from the head of the queue, starts the timer, and transfers control to the job. If the job is 2 microseconds long, it finishes execution and transfers control back to the monitor. The monitor picks a job from the head of the queue, starts the timer, and transfers control to the job. If the job is 7 microseconds long, the timer expires after 5 microseconds. The monitor takes control back and places this unfinished job at the tail of the queue. After some time, this job comes to sit at the head of the queue, and this time it completes. In time sharing systems, when the timer expires, control is automatically transferred to the monitor and the current job is said to be preempted. Preemption means taking the processor forcibly away from a user job. The monitor then transfers control to the job at the head of the queue. The size of the quantum is small, and this results in very fast interleaving of execution of multiple user jobs, which generates constant activity at all user terminals attached to the mainframe. This makes each user believe the processor is working on his job. When a job asks for I/O, control is transferred back to the monitor, which starts the I/O operation, resets the timer, and passes control to the job at the head of the queue. Some people might confuse the time slot of a time sharing system with the timer we used in the simple batch system. The two things are entirely different. The timer in simple batch systems is meant to go off if a job does not leave the processor for a very long time. When this timer goes off, the job is aborted. The owner of the job will have to recode the job so that it uses lesser time. In time sharing systems, when the time slot expires, all the work that the user job had done so far is stored and the job is placed at the end of the queue. When the job gets to run again, its incomplete progress is restored in the processor's registers and it starts from where it left last time. I have been using the word monitor, but you must have understood that what began as the monitor became the OS we know. So if we look back, first we had serial processing systems with no operating system, which were very difficult to use. Then we introduced OS and created simple batch systems. They had the monitor and a user job in their memory. When the user job asked for I/O, the processor sat idle, and this was bad because who would want to waste precious computing time of an expensive machine? Then we started keeping the OS and more than one jobs in the memory. Now, when a user job asked for I/O, the processor would switch to another job. Still, since only one job executed at a time, other users experienced long waiting times after job submission. So, we started interleaving multiple user jobs very quickly, executing a bit of one job, then a bit of the other, then a bit of yet another. This made the user experience much better. Here we finish the evolution of computers. What did we learn? A machine cannot be run efficiently without an operating system. The operating system must not be altered by user programs. All I/O must be managed by the operating system. Keeping more than one user jobs in memory reduces the processor's idle time. Interleaving jobs and switching between them at a fast rate improves user experience and reduces response time of the machine. If you notice the systems around you, the smartphones that you have or the desktop PCs that you have, all computers have well developed operating systems, and all of these systems use multi-programming and time sharing techniques. So, students, this was all about operating systems and their history. Let's talk about the things that I want you to do after you've listened to this lecture. Read the book. Keep the Word file that you created with you. I will ask you to submit it in Google Classroom. Write your questions on a piece of paper and keep it in front of you during the online session relevant to this lecture, and I will be answering your queries in this session. If you have suggestions relevant to content or quality of the lecture, please email them to me. We will meet again in the online session and in the recorded lecture. Till then, Allah Hafiz.